Yeah, good morning, students. So today we would like to discuss regarding this self-learning topic on resource limitation and performance evaluation. So now I would like to share my screen. So the self-learning topic is on resource limitations and performance evaluation. So the lecture objectives are: this session will develop the students' knowledge on concepts of resource limitation while instruction execution is pipelined, and another one is the performance evaluation. Okay, so the resource limitation, we already had a discussion regarding this pipelined execution of the instructions, so which will enables the execution of the instructions in a overlapped manner, but the pipeline stalls when there are insufficient hardware resources to permit all actions to proceed concurrently. For example, if we have two instructions, each needs to access the same resource in the same clock cycle. Anyway, ultimately, the one instruction must be stalled so that other instruction can utilize that resource. So this can prevent by providing an additional resources. So if both fetch and memory stage of the pipeline are connected to the cache memory, then it is not possible for activity in both stages to proceed simultaneously. Normally, the fetch stage accesses the cache in every cycle. However, this activity must be stalled for one cycle when there is a load or store instruction in the memory stage also requires to access the cache, because this fetch stage, when we are executing load or store instructions, it requires minimum two clock cycles are required, that we have seen, as well as when we are writing this data into the memory. So memory operation, when we are doing that, we need to access both cache also, we need to access that. So that is the reason it requires two clock cycles are required here. For example, if you take a particular task which consisting of set of instructions, and these set of instructions, out of that we have, there are 25% of instructions are load or store instructions. Out of that total n number of instructions, 25% are the load and store instructions. Then these load and store instructions creates the stalls, so thereby increase the execution time of the program by 25%. So using separate cache for instructions and data, okay, if you are using separate cache for instructions and data, allows the fetch and memory stages to proceed simultaneously without stalling. That is one solution where we can overcome this time which is required for this execution, which increases as a result of these stalls. Then next, coming to this performance evaluation. So we already had a discussion regarding this non-pipelined processors. What is the execution time of a program? So generally the execution time of a program in a non-pipeline processor has a dynamic instruction count of n, and which is given by n into s divided by r, where n is the instruction count and s is the average number of clock cycles it takes to fetch and execute one instruction. Okay, s is the average number of clock cycles that it requires to fetch and execute one instruction, and r is the clock rate. R is the this is a clock rate. So that means how many clock cycles per second. So this equation is generally referred to as a basic performance equation. Okay, so that is the number of instructions into the average number of clock cycles it takes to fetch one instruction divided by the clock rate, that is the clock cycles per second. This is called it as a basic performance equation. Another useful performance indicator is the instruction throughput. So which is the number of instructions executed per second. So for non-pipelined execution, the throughput PNP is given by an equation which is equal to R by S. Okay, so you all familiar with that. The processor which is not pipelined, then in that throughput is nothing but the R clock rate divided by the average number of clock cycles, which is called it as a throughput. Next, coming to this another point, the processor presented in earlier chapter, we already had a discussion regarding how the instruction execution will be there. We all familiar that there are 5 cycles to be followed by an instruction to execute. So thus there are no cache misses, then S is equal to 5, because 5 clock cycles are required to execute completely that particular instruction. The pipelining always improves the performance by overlapping the execution of successive instructions, so which increases the instruction throughput even though an individual instruction is still executed in the same number of cycles. So for this 5-stage pipeline, each instruction is executed in 5 cycles, but a new instruction can ideally enter the pipeline during every clock cycle. Thus, in the absence of stalls, S is equal to 1, and the ideal throughput with pipelining is RP is equal to P, R is equal to R, because S value is equal to 1. In an ideal situation, the throughput with the pipeline. A 5-stage pipeline can potentially increase the throughput by a factor of 5. Okay, in general, if we are following n-stage pipeline, which has the potential to increase the throughput is n times. So thus it would appear that higher the value of n, larger the performance gain because the throughput is increased. Anytime a pipeline is stalled or instructions are discarded, the instruction throughput is reduced below its ideal value. Hence, the performance of a pipeline is highly influenced by factors such as stalls due to data dependencies between instructions and penalties due to branches. Cache misses increases the execution time even further. So these are the factors which will influence the performance of the pipeline. So we will now see the effect of stalls and penalties, how we can calculate that. So to evaluate the effect of stalls not related to cache misses, so that means we are assuming that cache it is only the case. So we can consider how often a load instruction is immediately followed by another instruction that uses the result of memory access. Earlier, we have seen that one cycle stall is necessary in such case. So while ideal pipeline execution has S is equal to 1, stalls due to such load instructions have the effect of increasing S by an amount of delta stall. So for example, assume that load instructions constitutes 25% of the dynamic instruction count and assume that 40% of these load instructions are followed by a dependent instruction. So a one cycle stall is needed in such cases. Hence, the increase over the ideal case of S is equal to 1 is delta stall is equal to 0.25 into zero point 0.4 into 1, which is equal to 0.10. That is, the execution time is increased by 10%. Okay, the execution time is increased by 10% and throughput is reduced to Rp is equal to P, P is equal to R divided by 1 plus delta stall, which is equal to R divided by 1 plus 0.10, which is equal to 1.1, so which is equal to 0.91 into R. So that is the throughput which is calculated. To evaluate the effect of stalls not related to cache misses, so we can consider how often a load instruction is immediately followed by another instruction that uses the result of memory access. Earlier, we have seen that a one cycle stall is necessary in such cases. Now consider the penalties due to mispredicting branches during program execution. So when both the branch decision and branch target addresses are determined in the decode stage of the pipeline, the branch penalty is one cycle. Assume that branches constitutes 20% of dynamic instruction count of a program and that the average prediction accuracy for branch instruction is 90%. In other words, 10% of all branch instructions that are executed incur one cycle penalty due to misprediction. The increase in the average number of cycles per instruction due to branch penalty is delta branch penalty is equal to 0.20 into 0.10 into 1, which is equal to 0.02. This is the branch penalty which is incurred due to misprediction. So the stars related to load instructions and the penalties from branch mispredictions are independent. Okay, so that is delta branch penalty and the delta stall both are independent. Delta stall is related to the load instruction penalty and this delta branch penalty is related to the branch mispredictions. Hence, their effect on performance is additive. That means we have to add these two quantities. And then next coming to this cache misses on performance, how you can estimate the cache miss on performance by considering the frequency of their occurrence. So for example, the time to access the slow or main memory is a penalty that starts the pipeline for PM cycles every time there is a cache miss. So a fraction mi of all instructions that are fetched incur a cache miss. A fraction d of all instructions are load or store instructions, and a fraction md of these instructions incur a cache miss. So the increase over the ideal case of s is equal to 1 due to cache misses is delta miss is equal to mi plus d into md into pm. For example, you consider this is a one scenario here we have given. Suppose that 5% of all fetched instructions incur a cache miss. 30% of all instructions executed are load or store instructions, and 10% of their data operand access incurs a cache miss. Assume that the penalty to access the main memory for a cache miss is 10 cycles. Then the increase over the ideal case of S is equal to 1 due to cache misses in this case is given by delta miss is equal to 5% means that 0.05 plus D, that is the 30% of all instructions executed are load or store instructions. So 0.30 into MD is nothing but 10% of their data operand access incur cache misses. So into PM assume that the penalty to access main memory for cache misses is 10 cycles. Okay, so the pipeline stalls PM cycles every time there is a cache miss. So that is the penalty that stalls that. So into 10, which is equal to zero point 0.8. This is the delta miss. So compared to delta stall for data dependencies and delta branch penalty for mispredictions branches, the effect of slow main memory for cache misses is more significant in this example. So when all factors are combined, S is now increased from the ideal value of 1 to 1 plus delta stall plus delta branch penalty plus delta miss. So the contribution of cache misses is often the dominant factor in this particular case. So now the learning outcomes are revisited here. So after completion of this particular self-learning topic, you are able to understand the concept of resource limitation in instruction pipelining and how the performance evaluation is depend on this branch prediction penalties as well as cache misses. So the lecture outcomes is that after completion of this self-learning session, you will be able to analyze the effect of stalls and the penalties in instruction execution in a pipelined manner. So thank you students.